Intelligent storage system. Business critical applications require high levels of performance, availability, security, and scalability. A disk drive is a core element of the storage that governs the performance of any storage system. Some of the older disk array technologies could not overcome performance constraints due to the limitations of the disk drives and their mechanical components. RAID technology made an important contribution to enhance storage performance and reliability, but disk drives, even with the RAID implementation, could not meet the performance requirements of today's application. Advancements in technology, a new breed of storage solution known as intelligent storage system has evolved. These intelligent storage systems are feature-rich RAID arrays that provide highly optimized input-output processing capabilities. These intelligent storage systems are feature-rich RAID arrays that provide highly optimized input-output processing capabilities. These storage systems are configured with a large amount of memory and multiple input-output paths and use sophisticated algorithms to meet the requirements of performance-sensitive applications. These arrays have an operating environment that intelligently and optimally handles the management, allocation, and utilization of storage resources. Support for flash drives and other modern-day technologies such as virtual storage provisioning and automated storage tiering has added a new dimension to storage system performance, scalability, and availability. Components of an intelligent storage system. An intelligent storage system consists of 4 key components: front-end, cache, back-end, and physical disks. An input-output request received from the host at the front-end port is processed through the cache and back-end to enable storage and retrieval of data from the physical disk. A read request can be serviced directly from cache if the requested data is found in the cache. In the modern intelligent storage system, front-end, cache, and back-end are typically integrated on a single port. We have the components of a single intelligent storage system represented using a diagram where we have the host and the intelligent storage system which is interconnected with a storage network. The intelligent storage system consists of a front-end, cache, back-end, and physical disk. The front-end contains port and front-end controller. The back-end contains ports and the back-end controller, where these remains interconnected. Front-end. The front-end provides the interface between the storage system and the host. It consists of 2 components, front-end ports and the front-end controller. Typically, a front-end has redundant controller for high availability, and each controller contains multiple ports that enable large number of hosts to connect to the intelligent storage system. Each front-end controller has processing logic that executes the appropriate transport protocols such as fiber channel, ISC-SA, FSCON, and FCOE for storage connections. Front-end controller route data to and from cache through the internal data bus. When the cache receives the right data, the controller sends an acknowledgement message back to the host. Cache. Cache is a semiconductor memory where data is placed temporarily to reduce the time required to service input-output requests from the host. Cache improves storage system performance associated with rotating disks or hard disk drives. Rotating disks are the slowest components of the intelligent storage system. Data accesses on rotating disks usually take several milliseconds because of seek time and rotational latency. Accessing data from cache is fast and typically takes less than a millisecond. On intelligent arrays, write data is first placed in the cache and then returned to disk. Structure of cache. Cache is organized into pages, which is the smallest unit of cache allocation. The size of the cache page is configured according to the application of input-output size. Cache consists of data store and tagram. The data store holds the data, whereas the tagram tracks the location of the data in the data store and in the disk. Entries in the tagram indicate where the data is found in cache and where the data belongs to the disk. Tagram includes a dirty bit flag which indicates whether the data in cache has been committed to the disk. It also contains the time-based information such as the time of last access, which is used to identify cached information that has not been accessed for a long period and may be freed up. Here we have a structure of a cache where the cache contains the page, data store, RAM, and we have the disk which remains connected to the cache. Read operation with cache. When a host issues a read request, the storage controller reads the tagram to determine whether the required data is available in the cache. If the requested data is found in the cache, it is called as read cache hit or read hit, and the data is sent directly to the host without any disk operation. This provides a fast response time to the host. It is about a millisecond. If the requested data is not found in the cache, it is called as cache miss, and the data must be read from the disk. The backend accesses the appropriate disk and retrieves the requested data. Data is then placed in the cache and finally sent to the host to the frontend. Cache misses increase the input-output response time. Now we have a diagrammatic representation for read hit and read miss. When you look upon the read hit, it means the data is found in the cache. We have the host, cache, and then the physical disk. Host is connected to cache is connected to physical disk. Okay, now the cache and host has read request and send data. So when we are able to find the data, it is read hit. Now when data is not found in the cache, after requesting from the cache, if it is not found in the cache, the request is sent to the physical disk. Then it comes to the cache and to the host. Now, a prefetch. A prefetch or read-ahead algorithm is used when read requests are sequential. In a sequential read request, a contiguous set of associated blocks is retrieved. Several other blocks that have not yet been requested by the host can be read from the disk and placed into the cache in advance. When the host subsequently requests these blocks, the read operation will be read hits. This process significantly improves the response time experienced by the host. The intelligent storage system offers fixed and variable prefetch sizes. In fixed prefetch, the intelligent storage system prefetches a fixed amount of data. It is most suitable when the host input-output sizes are uniform. In variable prefetch, the storage system prefetches an amount of data in multiples of size of the host request. Maximum prefetch limits the number of data blocks that can be prefetched to prevent the disks from being rendered busy with prefetch at the expense of other input outputs. Read performance is measured in terms of read hit ratio or the hit rate, usually expressed as a percentage. This ratio is the number of read hits with respect to the total number of read requests. A higher read hit ratio improves the read performance. Write operation with cache. Write operation with cache provides performance-based advantages over writing directly to disks. When an input-output operation is returned to the cache and acknowledged, it is completed in far less time than it would take to write directly on the disk. Sequential writes also offer opportunities for optimization because many smaller writes can be coalesced for larger transfer to disk drives with the use of cache. A write operation with cache is implemented in the following ways. The first one is write back cache. Data is placed in cache and an acknowledgement is sent to the host immediately. Later, data from several writes are committed to the disk. Write response times are much faster because the write operations are isolated from the mechanical delays of the disks. However, uncommitted data is at risks of loss if cache failures occur. Write-through cache. Data is placed in the cache and immediately returned to the disk, and acknowledgement is sent to the disk. Because data is committed to disk as it arrives, the risks of data loss are low, but the write response time is longer because of the disk operation. Cache implementation. Cache can be implemented as either dedicated cache or global cache. With dedicated cache, separate set of memory locations are reserved for reads and writes. In global cache, both reads and writes can use any of the available memory addresses. Cache management is more efficient in global cache implementation because only one global set of addresses has to be managed. Cache management. Cache is finite and expensive resource that needs proper management. Even though modern intelligent storage systems come with a large amount of cache, when all cache pages are filled, some pages have to be freed up to accommodate new data and avoid performance degradation. Various cache management algorithms are implemented in intelligent storage systems to proactively maintain a set of free pages and a list of pages that can be potentially freed up whenever required. Now, methods. Least recently used. An algorithm that continuously monitors data access in cache and identifies the cache pages that have not been accessed for a long time. Least recently used either frees up these pages or marks them for reuse. This algorithm is based on the assumption that data that has not been accessed for a while will not be requested by the host. Most recently used. This algorithm is the opposite of LRU, where the pages that has been accessed more recently are freed up or marked for reuse. This algorithm is based on the assumption that recently accessed data may not be required for a while. Flushing. Flushing is the process that commits data from the cache to the disk. On the basis of input-output access rate and pattern, high and low levels called watermarks are set in cache to manage the flushing process. High watermark is the cache utilization level at which the storage system starts high-speed flushing of cache data. Low watermark is the point at which the storage system stops flushing data to the disks. Idle flushing occurs continuously at a modest rate when the cache utilization level is between higher and low level watermarks. High watermark flushing activated when cache utilization hits the higher watermark. The storage system dedicates some additional resources for flushing. This type of flushing has some impact on input-output processing. Forced flushing occurs in the event of a large input-output burst when cache reaches 100% of its capacity, which significantly affects the input-output response time. In forced flushing, system flushes the cache on priority by allocating more resources. So we have a diagrammatic representation of idle flushing, high water flushing and forced flushing.